Okay, let's start section 4 of chapter 7. The section is titled Parallel Lines and Proportional Parts. The goal here is to use proportional parts within triangles and use proportional parts within parallel lines. Okay, new vocabulary, you should have already looked this up in the beginning of the chapter, but a mid-segment of a triangle is a segment that you draw between midpoints of sides of the triangle. So I tried to draw this as a midpoint. I sketched this. It wasn't a great sketch. But here I'm trying to show that this segment, and specifically this one here, is the mid-segment. I'll try to make it in another color. That's the mid-segment because it's connecting midpoints. Okay, first theorem we're going to look at. If a line is parallel to one side of a triangle and intersects the other two sides, then it actually divides those sides into proportional lengths. Now, we've already looked at this. We've already seen that angle A is equal to itself, congruent to itself by reflexive property. And if these two segments here are parallel, then these angles are congruent because of corresponding angles. And either third angles or corresponding angles, these two angles are congruent. So therefore, by angle, 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 the small triangle is similar to the big triangle surrounding it. So let's take a look at some segments here. Okay, let's write a statement of similarities. So we've got triangle ABE is similar to what's corresponding to A is itself, A. What's corresponding to B is, I'm getting cut off over here, is C, and E is corresponding to D. All right, so we can write a proportion on these sides here. AB is to AC as AE is to AD. Well, let's replace AC using the segment addition postulate. AC is actually equal to AB plus BC. And likewise, AD, this other big side, is equal to AE plus ED. So let's substitute in here. We've got AB over here. We're not touching that. We're replacing AC with AB plus BC. And AE we're going to leave alone, but we're going to replace AD with AE plus ED. All right. So now if we cross multiply here, we can do that easily. We've got AB times this whole sum, AE plus ED. And likewise, this side cross multiply, we have AE times the sum AB plus BC. I got to represent that in parentheses. Now we can use the distributive property. We have AB times AE plus AB times ED equals AE times AB, so we're multiplying here, plus AE times BC. Well, what do you notice here? We've got AB times AE over here, and we've got AB times AE over here. So if we subtract that from both sides, then what happens? It cancels or reduces out. So we have left AB times ED equals AE times BC. Okay, I'm going to divide both sides by BC. I can do anything I want here as long as I'm consistent. So I have this expression over here, AB times ED divided by BC. Over to the right, my BC divided by BC reduces to 1. Now I'm going to divide both sides by ED. And over here, my ED divided by itself reduces to 1. And so what I end up with is AB divided by BC is equal to AE divided by ED. And that's what this whole theorem is about. That, in fact, if we go back up here, we can see that these sides are proportional. AB is to BC, this little segment, it's not the side of a triangle, it's the segment, is proportional to AE is to ED. That's what we just proved in this theorem. Now, this theorem is very useful to know. However, you can get away without it. We could always write all the corresponding sides. So you can always continue to write AE is to this whole length, AD. But knowing these pieces are proportional can be very helpful. Now, the converse of the same theorem is also true. If you find that these are proportional, these side pieces here are proportional, then you can conclude that these lines here are parallel. So in the previous page, we were told the lines are parallel. We used that information to, by angle, put together proportions that proved that not only are these sides of the triangle proportional, but these segments are as well. We're going in the opposite direction now. If these pieces are proportional to each other, then these sides must be parallel. Why is this beneficial? So take a look at this problem here. What we have is two parallel lines, and so by angle, the little triangle is similar to the big triangle by angle. We know that these pieces, these sides, are proportional, and we know that this side to the whole triangle is proportional. Since we know these pieces, we could always set up the full side lengths here. We could say that SV is that whole side, SR, as SU is to the whole side, ST, and we could substitute and solve. But we also now know that SV is proportional to this segment, VR, as SU is to UT. And I'll let you substitute and solve. Okay, and the rest of your notes have various problems where you're going to use this new theorem, or not. You could still always set up a proportion BX here to the whole side of the triangle, BA, BY to the whole side of the triangle, BC. Or you can set up these pieces of proportions if you'd like. Okay, now we're going to take a look at the converse of the triangle proportionality theorem. And that states that, well, basically the converse is trying to prove whether or not these segments are parallel. And we can prove that they must be parallel if these pieces here, these segments, are proportional. So let's take a look at this problem. DH is 18 and HE is 36. So clearly this is not drawn to scale. And we're told that DG is 1/2 of GF. So let's call this X. If that's 1/2 of this piece down here, we could call this 2X. All right, let's see if they are proportional. So we are trying to see, is DG to GF equal to DH is to HE. So we've got substitute X is to 2X as 18 is to 36. And of course our X's reduce out, so we have 1 to 2. Is that the same thing over here? And it is. So they are proportional, and we can conclude that these two segments must be parallel. So we can mark those as parallel as a conclusion. Next problem is very similar, so I'm going to let you use the converse theorem here to prove these lines are parallel on your own. Okay, let's take a look at a new theorem, the triangle midsegment theorem. The triangle midsegment theorem states that if you do draw a midsegment connects midpoints, so J and K are midpoints. If you do draw that midsegment, then two things happen. One, it must be parallel to FG. JK must be parallel to FG. And as it turns out, JK is half the length of FG. So let's try to see if we can prove that. All right, we are going to say, well, let's just assign a variable here. HK, let's say that's X length long. If K is a midpoint, then KG is also X length. And over here, let's say JH is Y in length, then JF is also Y, because those are midpoints. They cut a segment into two equal halves. Now, let's look at the small triangle and the big triangle, not the pieces, okay? This proportion here, yes, they are proportional, but it will be at a different proportion for these segments. If we want to look at the bottoms or the tops of this triangle, the small triangle and the big triangle, we got to use the whole sides here. All right, let's see what I'm talking about. We're going to say that HK in the small triangle is to the length of the big triangle, HG. We know that is proportional to HJ is to the big triangle, HF. And that is to the same proportion as the third side. KJ is to FG. They are all proportional. So HK, as we've drawn it, is X, and HG is X plus X, or 2X. Over here, we have Y, and the whole length will be 2Y. And we are saying that that is the same as KJ. I'm going to use JK instead here, since that's what was used above, is to FG. Well, our X's and Y's are going to reduce out, so we have 1/2 equals 1/2 equals JK over FG. So we can solve for JK, and we can see easily by cross-multiplying that JK is 1/2 the length of FG. All right, let's try to use this mid-segment theorem here on this problem. In the figure, DE and EF are mid-segments. So let's mark that. DE is a mid-segment. That means E is a midpoint. D is a midpoint. If E is a midpoint, AE is congruent to EC. If D is a midpoint, BD is congruent to DC. EF is also a mid-segment, so E is a midpoint, F is a midpoint, and that means AF is congruent to FB. Now, we were told with this theorem that the mid-segment is half the length of the line that it's parallel to. So here, find AB. AB here is going to be parallel to ED, and AB is going to be twice the length of ED. If ED is 5, then AB is going to be 2 times 5, or 10. Find FE. FE is a mid-segment. It's going to be half the length of the line it's parallel to. The line it's parallel to is 18 units long, so this is going to be half that, or 9. Half of 18. And finally, find the angle AFE. AFE. That's going to be this angle here. I'm going to put it in red. That angle here. Well, we know by the theorem that this mid-segment ED is going to be parallel to AB. So this angle X, which is AFE, is alternate interior to that 87 degrees. So these two are going to be congruent. So this angle is going to be 87 degrees. The problems. I think you can all do this on your own as well. Now, proportional parts of parallel lines. This is kind of confusing, but if you will, just kind of look at these parallel lines here, AE, BF, and CG. What ends up happening here when you have a lot of parallel lines, or even just two parallel lines, it creates proportionality. So if you can imagine, these lines here will eventually intersect, creating triangles. Small triangles and then bigger triangles within them. So the same type of proportionality, triangle proportionality that we've been looking at so far, will apply here. And what you can see is that AB, this segment, is, 2BC is proportional to EF is to FG. So that's what's seen here. So basically these segments that are created by the parallel lines will be proportional as well. So let's take a look at how we use this information. In this problem, we have some parallel streets. Larch Street, Maple Street, and Nuthatch Street are all parallel. And then we have two transversals coming in here. The figure shows distances in between the city blocks, and they want you to find this distance right here. And by that distance, it's really this length here. So, as I'd mentioned on the previous theorem, these segments that are created, in fact you could even see the triangles here, they will be proportional. So the same type of proportionality applies. So we could say 13 is to 26 as 16 is to x. And you can cross multiply to find that unknown length. In this case, since you do have two triangles that are being created, and you know that these are parallel, then you could just as well write a different proportion. You can say 13 is to 13 plus 26, so this whole length here, and that would be 39, as 16 is to 16 plus x. And you should arrive at the same answer. Okay, and here is another type of problem there where we have parallel lines coming through here, Davis, Broad, and Main, creating proportional segments here with the transversals. So you can try and practice on this problem. And finally, congruent parts of parallel lines. This is a corollary. That's kind of like an add-on. And what this says is if they are parallel, these lines, and you've got these transversals coming in, if these segments that are created are actually congruent as AB and BC are being marked, then these other segments over here, EF and FG, will also be congruent. And that's not something I think you really have to memorize, because you could find that out pretty easily by setting up a proportion. And here is a more algebraic example, and instead of getting rid of the solution and how this is found, I thought I'd just keep this in here. The parallel lines are coming in, and these pieces are going to be proportional. Now, because these are marked congruent, you can see we have two unknowns here, y and an x. Because these are marked congruent, you can easily solve for x by putting these two expressions equal to each other. And if these two are congruent and these lines are parallel, then you know that these segments are also congruent. And you could put 9y minus 2 equals 6y plus 4 and easily solve for y. And I'm going to let you practice on this problem. And I think that's the end of the video. Thanks for listening. Take care.